Okay, so assalamu alaikum everyone. My name is Noha Alnaser. I'm a second year medical student. And today, inshallah, we'll be discussing kidney sectional function and mass clearance, which are the two first physio lectures. Now, these might be some like simple lectures. Inshallah, you guys will find them that way as well. But if you grasp the concepts in these lectures really well, they build a really good basis for you to, approach the upcoming lectures, which are a bit more challenging. So I do urge you to try and focus with me as much as possible. I will be having checkpoints and questions throughout the slides. And everything that is bolded and highlighted in pink is what I consider to be important. So try to, focus on these. And I try to include everything from the slides and transcription and recording. So studying the Spanish should be sufficient along with some practice questions, inshallah. Okay, with that being said, let's get started. So the objectives that we will be covering today would be defining some terms like filtration, reabsorption, secretion, excretion, how they're all interconnected. We will explain the clearance principle and we will go over equations and formulas that help us measure some important renal physio concepts. So first of all, I want to go over broadly over what the function of the kidney is. Now, the entire renal physio blog is basically going to go through all of these in depth. But it's good to have some kind of broad view on what the kidney does generally. So it's four main functions, which would be clearance of blood of waste products, regulation of water and electrolytes, hormone secretion, and maintenance of acid-base balance. So the first thing is clearance. Now, you already know from from your biochemical, from your biochemistry that we have a lot of biochemical reactions that take place in our bodies, and usually after these metabolic, reactions take place, we have a lot of end products. Now, these end products must be excreted, otherwise they will accumulate, and that will be really detrimental for the body. So an important, for example, amino acids, after they get broken down, you have urea. Muscle creatine, after it gets broken down, you have creatinine. And therefore, in other stuff like nucleic acids or uric acid, for all of these should be excreted out of the body. And the most important ones that you need to focus on would be urea and creatinine, and you'll see why soon, inshallah. And also the kidney clears the blood of drugs. So for example, you take a Panadol, after a while, your body must excrete that Panadol out. So drugs, pesticides, all other chemicals, etc. Usually the kidney eliminates these substances from the body at rate equal to the production rate. So for example, if you make a certain amount of urea per day, that urea must be excreted as well. Okay. If someone has the mic open, please make sure to turn it off. Thank you. Okay. The second function of kidney would be regulation of water and electrolytes. Now we know that the body is mainly made up of water and ions, sodium, potassium, bicarb, hydrogen, iron, whatever, okay? Now the kidney must control the body fluid osmolality, which is really important for normal cell volume. And it also regulates the iron concentration in the body. So to maintain this balance, the daily intake of the electrolytes must always equal the excretion of electrolytes. You guys can see that we're really focusing on maintenance and steady conditions and homeostasis, because if the body goes out of these controlled environments, it goes haywire. So for example, the intake of an electrolyte, let's say like sodium, is more than its excretion, then you will have a lot of sodium in your body, and that is called a positive balance for sodium. Okay, if you have, for example, and vice versa. So for example, if your excretion for sodium is more than your intake for sodium, then you have too little sodium in your body, and that is called a negative balance for electrolytes. Okay. The third function for kidney would be the hormone secretion. Now, the three hormones that I want you guys to focus on would be erythropoietin, renin, and vitamin D. Erythropoietin, you know from your HLS that it is the one that stimulates the synthesis of erythrocytes, red blood cells. Renin, which is involved in the renin-angiotensin-aldosterone system, which you guys will discuss in much more detail later on. And finally, we have vitamin D, which is, more specifically, it turns vitamin D from one form to another by an enzyme, but you guys don't need to know that. Just know that it's vitamin D or also cholesterol. Okay, so cholesterol is another name for the vitamin D form. Okay, and the final function for the kidney would be the acid-base balance. We know that the body must maintain a really specific pH, around 7.45. If it ever goes out of that pH, everything will basically just crumble, because all the body's metabolic functions are dependent on the pH. And the lungs, lungs, liver, and the kidney, most importantly, are the ones that are regulating this acid-base balance. So it's really important to maintain it. And you guys will have the last two physio lectures focusing just on this. Okay, so now that we have a broad view on what exactly is the kidney, not exactly, just a broad view of what the kidney does, let's discuss more of its morphology and how does it look like. Taban, you will discuss this more in detail in your anatomy and histo But generally, we divide the kidney into three parts. We have the cortex, which is the outer part. Let me turn. Okay. Cortex, which is like the most outer parts. Then we have the medulla, which is divided into two parts. Medulla could be divided into outer parts and inner parts. Okay. So let's say this is outer and this is the inner. Okay. So again, cortex, outer medulla, inner medulla. Okay. And we have these tiny tubes. Okay. These tiny tubes are called a minor calyx. Once they join together, so when two minor calyxes join together, like this one, for example, this one, it forms like a major calyx. Okay. These calyces, okay, are the ones that indicate when the urinary tract begins. So once the calyces, like the major, minor, and major starts, this is when the urinary tract begins. And one thing to note is once the urine reaches the urinary tract, it no longer changes composition. Whatever changes that have happened to the urine have already been done before that. Okay. The nephron is the functional unit of the kidney. Now, the nephron, do you see like these like weird like yes, these lines right here, these are the nephrons. Okay, we will discuss them in more detail now. I'll zoom in and show you guys. But mainly, every kidney has about 2 million nephrons. So technically, you have a total of 4 million nephrons in all of your kidneys. Okay, the two kidneys. Another really important, like concept that I need you guys to make sure that you're okay with is that we have one door in and two doors out. So the renal artery is the only input source into the kidney. So whatever is going to ever enter the kidney is only entering through the renal artery, and whatever is going out of it is going through either the renal vein or the renal pelvis. Okay, which technically the ureter. So like the urine. So the renal arterial blood is going to it's going to be the only source into the kidney, and then the venous blood is going to take out along with the urine everything that has entered. So again, one door, which is the renal artery, and one door in renal artery, two doors out, the renal vein and ureter. And another concept is mass balance, which basically means that the amount of substance that has entered through the renal artery must equal the amount of substance that has left through the renal vein plus the ureter, or through like the urine. So again, whatever is entering through the renal arterial blood must equal the amount of substance leaving through the renal venous blood and urine. Okay, and as you guys can see, everything in pink is really important. Okay, so please focus on these. But moving on, let's like zoom into this nephron right here, like all the lines, these lines that I showed you here. If we zoom in, we'll get this. And I know this might seem a little intimidating, but we'll go through it step by step. Inshallah, you guys will get it. Okay, so when we start, remember this renal artery that we had right here? Let's say that this renal artery will give off little tiny branches for every nephron in the kidney, okay? And these branches we will call the efferent arteriole. Now, when you hear the word efferent, I want you to think of something going in, okay? So efferent is in, and efferent is out, okay? So we can see that the efferent arteriole is going in, and it's forming this sort of capillary, and then it's going out as the efferent arteriole. So in efferent, and out efferent, okay? When the efferent arteriole enters, it forms this capillary, and this capillary is called the glomerular capillary, okay? The glomerular capillary is surrounded by a capsule called the Bowman's capsule, and the tiny space in between the glomerular capillary and the Bowman's capsule is called the Bowman's space, okay? So again, efferent arteriole going in, efferent going out. In the middle, we have the glomerular capillary surrounded by the capsule, the Bowman's capsule, and the space in between is the Bowman's space, okay? Now we can, this is where we have the filtration barrier, okay? So after this point, this is the exact filtration barrier. And now we start with the tubules themselves. From the word tubule, it's like they're all tubes, okay? So the first tube we start with is the proximal tubule, because proximal is close to the glomerular capillary, okay? So the proximal tubule is divided into two parts, okay? We have the convoluted and the straight tubule. So convoluted is kind of like coiled, okay? We can see it's kind of coiled. And then straight is a bit more straight, okay? After that, we have the loop of Henle, okay? Or like Henle's loop, whatever you want to call it. So the loop of Henle is divided into two parts. We have the descending loop of Henle and we have the ascending loop of Henle, okay? The descending is only a bit thin, okay? So we call it the thin descending loop of Henle. On the other hand, the ascending is divided into both thin and thick, okay? So these are the loop of Henle's. After that, we have the early distal tubule and the late distal tubule. So this is like the beginning early distal, and then this is the late distal. You guys will see that we have like some extra names and labels on the side, but I honestly don't want you to like focus on these a lot because they're not really important for physio. You will go over them in much more detail in histo, and it would all make sense there. But for now, just remember that we have early distal tubule and late distal tubule, okay? And finally, we have the collecting duct, which technically is not really part of the nephron, but we just we treat it as such just to make things easier and more simple for us in physio-wise, okay? So let's go over this quickly again. We start off with the efferent, which is in, and then efferent is the one that is going out. And then we'll have the glomerular capillary, Bowman's capsule surrounding it, Bowman's space, that is space in between, We start with the tubules. After we finish with the filtration barrier right here, we have the proximal tubule divided into convoluted, which is coiled. We have the states right here. We have the loop of Henle, which is divided into descending and ascending. Descending is only ever thin, and ascending is both thin and then thick. Then we start with the early distal tubule, late distal tubule, and eventually we have the collecting ducts, which is not really part of the nephron. And as you can see from at the background, we have like cortex, the outer medulla, the inner medulla that I told you guys about. And this is why we also call it like the outer and inner medullary collecting duct, because then the outer and inner medulla, okay? Just a question, am I going too fast? Because I have a tendency to do that. Are you guys catching up fine, or should I slow down? Okay, that's good to hear. Moving on, let's have like a little battle between all the organs in the body versus the kidney. Now, as you guys can see here, I mentioned that all the organs have about 4,000 liters of plasma running through them. Now, the reason I'll be saying plasma all throughout the session is because we don't really consider blood as the one that is passing through the filtration barrier, because we know that blood is mainly consisting of two parts. Right? We have, this is the actual plasma, and then we have the like cells, generally red blood cells, white blood cells. The plasma is basically making up 60% of the blood, while the cells are making up 40%. When the blood passes through this glomerular capillary, the cells can never pass through because of the filtration barrier. They're too big to pass through the barrier, okay? Only ever the plasma passes through. So you'll see me only like mentioning the plasma, because cells we just completely disregard them. They're insignificant for us in the kidney, okay? So we have about 4,000 liters of plasma running through all the organs collectively per day, okay? Of this, we have about 20 liters that is being filtered, 18 that is reabsorbed, and 2 that is being uptaken by the lymphatic system. And I'm pretty sure you guys had like a picture of that in your CVP about showing like 20 liters filtered or something like this, okay? And then generally when we talk about like the filtration, we have the capillary, okay? So at the beginning of the capillary, we start off with the filtration, and then at the end we have the reabsorption. So this is a reabsorption site, here is the filtration, okay? And you guys can see that because we have like about 4,000 liters of plasma passing through and only 20 liters filtered, the ratio is kind of like really little. Like we're really filtering a tiny bit of all the plasma flow that is going through all of the organs, okay? And the reason for this like tiny amount is because of the function, because of the purpose of the filtration. Here we only ever care about the transportation of nutrients, and when we filter the plasma, it's making it easier for us to transport the nutrients to the cells. And this is why there's a huge discrepancy between the amount of plasma running through and the amount of the plasma that is actually being filtered, okay? Keep in mind that all of the values here, you guys don't have to memorize them. This is just like for your information and to make sense of the bigger picture. On the kidney though, you have to memorize all of this, okay? So first of all, you have about 120 milliliters per minute of plasma running through it, or technically 800 liters per day. I'm gonna be continuing with this value right here to have some consistency, okay? So out of this 800 liters of plasma running through the kidney per day, 20% of that is being filtered. 20% is going to be 180 liters. And then 180% of that filtered plasma is actually being, 99% of the 180 liters is actually being reabsorbed. So again, we have 800 that is passing through, 180 that is being filtered, and then 179 that is being reabsorbed, okay? Because we said 99% of it, okay? Fine. Now, a really, really important, like this, you guys have to memorize this really well. Filtration is in the glomerular capillary and reabsorption is in the peritubular capillary. And I'll explain this in a minute. But always remember that filtration and reabsorption are happening in different sites, okay? Now we have a lot of filtration relatively to the plasma flow. Like see how we had only 800, but we filtered 180 out of that. So it's much bigger than like the 4,000 to 20 ratio, right? And the reason for this is again, the function or the purpose of the filtration. Here in the kidney, we care about cleaning the blood, which explains the huge amount of plasma that's passing through it. Okay, so again, I want you to memorize all of the values right here because you'll be tested on it heavily, everything that is in pink. Okay. So now let's go over some general principles that are like about the kidney. As I mentioned, the filtration and reabsorption are happening in separate capillaries. Okay, well, you know how I mentioned we have the renal artery, right? And it sends off little tiny arterioles to every nephron, and these are called efferent arterioles. They're going in, efferent is going out. In the middle, we have the glomerular capillary, and then this is the Bowman's capsule. Okay. طيب, the efferent artery when it finishes, when it like leaves, you guys can see that it's basically leaving and it's forming a whole different system of like a capillary. And this capillary is called the peritubular capillary. Now, if we break down the word itself, peri means around and tubular means like tubes, right? So it's basically the capillaries that are around the tubes. They're the capillaries around these tubes, okay? So again, efferent going in, efferent going out, efferent goes out and forms the peritubular capillaries that are surrounding the tubular system itself, okay? So here is where we have the filtration and here is where we have the reabsorption, okay? Remember, this is really important. Filtration is in the glomerulus, like a glomerular capillary, and then reabsorption is in the peritubular capillary. Okay, so in the glomerular capillary, yeah, that's the same thing. We just mentioned how basically plasma is being filtered. It's never cells because cells are too large to pass through the filtration barrier, okay? Another thing you should remember is that we have about 65% of the water in the solutes that are being reabsorbed in the proximal tubule. So remember when I mentioned this tubule right here, this like pink part? This pink part is the proximal tubule, where 65% of the reabsorption of water in solutes is happening. And then after that, we have the loop of Henle, where 15% of the solutes and solutes are being reabsorbed. And then finally, we have 20%, which is variable. Just memorize these percentages, they're really important. Now, the reason I mentioned it's variable, I'll go over this in a second. But another thing that I need to remember is that we have the permeability to water, which is also variable across the nephron. So I mentioned that the proximal tubule will always be permeable to water. And this explains why we have like 65% of the absorption. If it is permeable to water, it's going to have the highest capacity to uptake the most water in solutes, right? The lobe of Henle is always impermeable for water. So you might ask, okay, you just mentioned that there's 15% that is being absorbed. So what exactly is it absorbing if there is no permeability to water? It's only solutes in the lobe of Henle, okay? So lobe of Henle always associated with solutes, okay? And finally, we have the distal tubule and collecting duct. Now, the reason I said the last 20% is variable is because it depends on a hormone, which is called the ADH or antithyrotic hormone, okay? If the ADH is present, then the distal tubule and collecting duct will be permeable. If the ADH is absent, then they will not be permeable, okay? And another really important concept is whenever I say fine regulation, always think of two systems, okay? Always two systems must come into mind. So either the nervous system or endocrine system. And here it's the endocrine because the presence or absence of the ADH is the one that's actually regulating the water reabsorption. And the ADH receptors and even like aldosterone, which is like another hormone you guys will discuss later, all the receptors for all these hormones are only in the distal tubule and in the distal tubule and in the collecting duct, okay? So this is basically the location of fine regulation. So whenever I say fine regulation, always think of the last thing, which is like the distal tubule and collecting duct. And this is why the last 20% of the water is variable. Because, for example, if you just had a bake and you have like a lot of salts in your system, obviously your body doesn't want to uptake more NaCl, right? Why does it need more salt? So there's no need for ADH, there's no need for the receptors, and we don't uptake the last 20%. On the other hand, if you have been running and you're very like low on water, then your body will release the ADH, there will be the receptors, there will be uptake of water because you are in need of this water. This is why the last 20% is variable, okay? Another concept that I want you guys to know is that if you want to double the urine volume, you can either do it by one of two ways, and you will very clearly see which one is more effective. The first way is to either double the JFR. Now, what exactly is JFR? JFR is the glomerular filtration rate. So remember when I said that we have the filtration barrier after the Bowman's space right here? So anything that actually manages to go through the tubules is called the glomerular filtration rate, okay? And we'll go over this much more, so you guys will get the concept at the end very well. So basically, this JFR, we can either double it from 800 liters per day to 1,600 liters per day to double the urine volume. You will do that eventually because you're doubling the JFR, so everything will be doubled, the filtration, the reabsorption values, everything will be doubled, and eventually you have a double amount of urine volume. But that's very tedious for the kidney, and that's very ineffective. So the other way that the kidney can do this is by decreasing the reabsorption. Remember when we said we start off with 800 liters that are passing through, 180 of which that are actually being filtered, and 99% of that is actually being reabsorbed. If we decrease this 99% to just simply 98%, we're going to get 178. 180 minus 179 is 1, and 180 minus 178 is 2, and 1 times 2 is 2. So this way, you actually double the urine volume by simply just decreasing the urine reabsorption by 1%, rather than doubling the GFR from 800 to 1,600. So what do you guys think? Which one is easier for the kidney to do, the first or the second way? Okay, yeah, sure. So basically, if you want to double the urine volume, the kidney can do it in one of either two ways, okay? So the first way is to simply double the GFR, which is the glomerular filtration rate. Glomerular filtration rate is basically everything that is being filtered through the Bowman's capsule and it's entering through the tubules, okay? Once this GFR is, is in the tubule, it's basically going to be reabsorbed, and you basically can, like, if you double the GFR from the normal 800 liters per day to 1,600 liters per day, you're actually gonna get double the volume at the end. It's just gonna be like really tedious for the kidney to go through all of this amount of GFR per day. It just doesn't make sense for the kidney to like filter double the amount just to increase the urine volume by double. So what it does instead is just decreases the urinary absorption from 99% to 98%. We started off with 800 liters of plasma passing through, right? And then 120 was being filtered, 800 liters of blood passing through, and then 120 plasma is being filtered. And eventually we get about 100, I'm so sorry guys, 180 liters, and then 179 is basically being reabsorbed, okay? So if we decrease this 99% to 98%, we're actually going to get 178 of the plasma being reabsorbed. So simply what I need you guys to remember, this might be all a little confusing, but all you need to remember is that the urine volume is regulated by the reabsorption and never the GFR, because it's much more convenient for the kidney to just simply decrease the reabsorption from 99 to 98 instead of doubling the GFR from 800 to 1,600 liters per day. Is that just clear, the last part where you just regulate the urine volume by reabsorption and not GFR? Okay. Okay, you're welcome. So this is the first checkpoint. We actually finished the first lecture, which is very simple and direct. Do you guys have any questions? Do you want me to go over the last part if it was a little unclear? Any of the concepts that we discussed so far that is still ambiguous for you guys? Okay, is everyone else also good with the concept so far? Should I go over anything else? Okay, I guess everyone's okay. That's good. Okay. Now let's move on to the second lecture. Let's start off with the structure model of the nephron. Now this is exactly the same thing, just like a different diagram. So remember when we said we have the efferent arteriole going in, and then we have the efferent arteriole going out, forming the peritubular capillaries, the capillaries that are around the tubules. And then we have the glomerular capillary in the middle. This is the Bowman's capsule, and the space in between is the Bowman space, and these are all the tubules. And finally, the collecting duct, okay? Now we're going to explain on this diagram the other concepts. So the first concept is mass clearance. Now, mass clearance is, first of all, these are some like abbreviations that you guys are going to see all throughout the block. So it's good to familiarize yourself with them from now. So RPF is renal plasma flow, RPFA is renal arterial plasma flow, RPFV is renal venous plasma flow, V with a little dot on top is the urine flow, and U is a substance concentration in urine, okay? So the first thing we must discuss in mass balance is the flow. Now, RPFA, we remember when we mentioned we have the renal artery. Whatever is entering the renal artery is basically going to go out through either the urine and the renal venous plasma, okay? So basically we say that the renal, renal plasma that is entering through the artery will equal the renal plasma leaving through the vein, as well as the urine itself, this is the urine flow again, okay? And because we mentioned that we have about 180 liters that are passing through the renal artery, and then 179 that is being reabsorbed. So technically, this 179 is leaving through the renal vein, and we're only excluding one. Remember the 1%, 1 liter that we did not, reabsorb. This one is basically the one that is passing through the urine. So 180 is really close to 179. So sometimes we just simply disregard it and we we don't say RPFA and RPFV, we just say RPF because the values are really close. And because the urine volume is just 1, it's kind of insignificant. So all in all, we just say RPF, okay? We don't confuse ourselves with RPFA, RPFV, and then the urine flow. It's all RPF because RPFA and RPFV are very similar, and the urine flow itself is insignificant. It's just 1, okay? So this is the first thing. Second thing is we have the amount of substances actually passing through the renal artery, okay? So basically the amount, remember always Dr. Shams mentions that the amount is basically the concentration times the volume, okay? So this is, you guys will see this all like in all Dr. Shams lectures. He really has to focus on that. So the amount is always concentration times the volume. Now the amount that is going to enter through the RPFA must equal the amount that is leaving through the RPFV and the urine, okay? So let's look at this. So RPF is technically the volume and PA is the concentration. Volume times concentration is amount, and we're talking about the amount of the plasma that's passing through the renal artery, okay? Because it's our only input, okay? After that, we have, again, same thing. This is the volume. This is the concentration. It's giving us the amount that is going out through the renal vein, okay? And finally, the urine flow here is the volume, and this is the U is basically the concentration, again giving us the amount of the urine itself, okay? So the amount of the urine plus the amount of the substance in the renal vein must equal the amount that has entered initially through the renal artery, okay? And if we play around with the equation a little and move it around, we basically can say that the cleared amount will equal to is equal to the excreted amount. So all that we did here is basically we took the amount of the plasma in the renal artery and minus it from the amount of the plasma in the renal vein, which gave us the excreted amount that is in the urine. Is that clear with everyone? Does that make sense? Okay. So simply all that we're saying here is that the amount in arterial plasma minus the amount of the venous plasma must equal the excreted amount. Okay, which is basically the urine. Type. Moving on, let's discuss clearance. Now, clearance might be like a tiny bit challenging concept, but inshallah you guys will get it. So clearance basically just means that the amount of substance X that is lost in the urine per time will equal the urine volume. It's like a lot of equations. And simply all that it's saying, the volume of plasma which has been cleared from substance X is called the clearance. So for example, let's say you have this is all of your plasma, okay? And you have this tiny bit of a substance that is in purple. If this substance in purple is cleared in the urine, then we say that it has been cleared from the plasma. That's simply it. You're just taking this substance from the plasma and moving it to the urine. And therefore, you have cleared the plasma of that said substance, okay? And basically, we have an equation for it. So remember we said this V on top is basically the urine flow. And then the U itself is basically the concentration of the substance, okay? And the PA is the basically the arterial plasma flow, okay? So basically the amount in urine is this, and the amount that is missing in plasma is basically the amount that will be found in the urine. So whatever you miss in the plasma is what you will get in the urine. And therefore the clearance is the volume of plasma that is cleared from a substance in a unit of time. So honestly, this equation itself, you guys should memorize it word for word because it will show up a lot. So this is what I need you guys to focus on. If you can write it on a paper next to you so we can solve the questions at the end. Okay, so clearance is simply urine flow multiplied by the urine concentration of the substance over the plasma concentration of that said substance. So let's say you have 100 liter of glucose and the urine flow is let's say 50 or whatever. And let's say you had in the plasma, let's say you had 500, whatever. This is exactly what we're trying to get at, basically. So just urine flow multiplied by the concentration of the substance divided by the concentration of the substance in the plasma. Okay. Type. Now, basically, how do we get all of these values in real life? Now, urine flow is very simple. All that you do is just you empty your bladder, wait for a certain time, and then empty it again, and then measure the amount of urine that you got in that specific time interval. So, for example, if you emptied your bladder at 1, and then you waited for 3 hours, and then you emptied it again at 4, then the amount you're gonna get when you empty your bladder the second time, over the time interval, which is basically 3 hours, is the urine flow. And for the concentration of X in the urine, it's basically really easy. We don't really concern ourselves with it. It's not important. But what's really important is the concentration of X in the plasma itself. So a lot of like substances in our body can actually fluctuate. It might not stay the same. We know how like glucose, if you take like a high carb meal, you're gonna have a lot of glucose in your plasma. But if you've been like fasting all day long, the glucose is gonna be really low. Therefore, to avoid this fluctuation and to make sure that everything we're measuring is actually like constant, we take either an endogenous substance under steady state conditions, or we infuse a substance. Okay. And I will give you examples for both of them. Now, why do we say infusion and not injection? Because an injection will basically increase the amount of blood itself, which will basically tweak the concentration. It will alter the concentration in ratio, and therefore it will confuse all the values. So we always say infusion and not injection. And infusion over a long period of time, so that after this period of time, you get a constant level of that basically substance. Okay. So just again to familiarize yourself with the abbreviations. V with a dot is urine excretion or urine flow. Ux itself is the concentration of the substance X, and Px is the concentration of X in the plasma. Again, it must be constant all throughout, so either an endogenous substance in steady state condition or an infused substance over a long period of time. Okay. Now, GFR is basically, as I mentioned before, it's the glomerular filtration rate, and it basically what makes up the tubular fluid. Filtration is simply the volume of fluid that is crossing the filtration barrier and entering the Bowman space. Okay. And basically, the filtered load of a substance is equal to the GFR multiplied by the plasma concentration. So whatever GFR you have multiplied by the original plasma concentration of the substance will give us the amount of substance that actually got filtered and entered through the tubular system. The reabsorption is simply just the movement. This is basically just showing the filtration itself, passing through the Bowman's space and entering to the tubular system. Reabsorption is simply when there is net movement of a substance from the tubular fluid right here into the peritubular capillary. So remember the efferent arteriole that gives us the peritubular capillaries? Basically, these substances will move from the tubular fluid into the peritubular capillaries, and that is called reabsorption. On the other hand, we also have like vice versa. So if the substance is moving from the peritubular capillaries into the tubular fluid, then that is called the secretion. And basically, we denote these concepts by certain abbreviations as well. So we have M with a dot on top and an I. So the M is the amount, and the dot is the time, while I is the reabsorption. And same thing here, we have the M with a dot on top and an S. M is the amount, dot is time, and S is the secretion. Okay. And basically, if we turn this into like an equation form, we basically can say that the excreted amount is equal to JFI, which is a filtered load. This is the amount, obviously. So this JFI here is the volume. This is the concentration, giving us the amount. And MS is, as we said, the secreted amount. MR is the reabsorbed amount. So the excreted amount equals the filtered plus the secreted minus the reabsorbed. So the excreted is equal to the filtered plus the secreted minus the reabsorbed. Okay. And basically, if a substance is neither secreted nor reabsorbed, so all of these values are 0, we just completely disregard them, we can say that the urine itself is equal to the filtered amount. Nothing really happened here, none of this happened. So whatever got filtered got excreted as well. Okay. And this substance can actually help us figure out something really important, which is JFI. If a substance is neither secreted nor reabsorbed, that means whatever is being filtered is whatever is getting out as well. And we know that what is being filtered is always a JFI. Okay, so we can say that, and if we put this in like a formula form, we actually get that JFI is equal to clearance, which is the urine flow multiplied by the concentration of the substance divided by the concentration of the substance in the plasma. Okay, and I'll tell you guys two substances that actually give us the exact JFI in a bit now. This is exactly what I said, just divided over a second slide. But that's the same thing. Excretion, again, is the net loss of a substance. And JFI could be found in this formula here, which is the urine flow multiplied by the urine concentration over the concentration in the plasma. Now, inulin clearance, basically, this is a substance that is infused. Remember when I said there's an infused substance that basically gives us the JFI? Where basically it's freely filtered and it does not get secreted nor reabsorbed. So whatever is being filtered right here is also being excreted. And this is exactly why it's beneficial, because it gives us a JFI. And we know JFI normally should be 180 milliliters. Therefore, inulin is, but like the only downside for inulin is that it's difficult to utilize because we have to infuse it. And instead of using inulin, sometimes we can actually use another endogenous substitute, which is creatinine. So again, just to go over this quickly, inulin is neither secreted nor absorbed. It is freely filtered, and therefore the amount that is filtered is the same amount that's excreted, and therefore we can measure GFY from inulin. And another substance, which is also an endogenous substitute, is the creatinine. Okay. So creatinine, the thing about it is it's endogenous. So it's made by you know how we have an end product in the muscle, and this end product is the creatinine. Creatinine is basically secreted a little and reabsorbed a little, but they're basically counterbalanced. So at the end, it kind of counts that as it was just simply freely filtered, and whatever got filtered is whatever got excreted. Okay, because the reabsorption and secretion kind of counterbalanced. If the production rate of creatinine is equal to its excretion rate, then we form a constant. Because creatinine is an endogenous substance that is being made in the body, the production rate will always equal the excretion rate. Therefore, we can just denote it as a constant that is M with a dot and creatinine. So all that you need to know is basically because creatinine is an endogenous substance, we just have a constant for it that we use in the formula. That's it, okay? And JFI is usually 120, and when the creatinine plasma concentration must be 1. So if creatinine plasma is 1, that's good. That means that the JFI is 120, which is the normal filtration. Okay. If JFI decreases, then PCR increases. It's inversely proportional. So we see here that PCR here is at 1, right? And this is the normal thing. And we get a JFI of 120. But if we decrease the JFI, as you move here, 175, 50, the creatinine plasma concentration actually increases. And that's bad because at some point, if it reaches around like 10 or something close to that, we need dialysis because it tells us that JFY is not sufficient. The kidney is not doing its job well. It's not getting rid of the toxic materials, so we require dialysis. The good thing about creatinine is that when you measure it, you only ever need the creatinine concentration in the plasma because we know that there's a constant, and the constant is going to be given in the question next time. It's fine. So you only need the creatinine concentration in the plasma. And another thing to note is that this relationship only exists if the production is constant. Meaning, if a patient, like if, for example, a doctor and a patient just exercised and they were at the gym, they exercised and they came to you, okay, and they're like, okay, check my creatinine clearance. They're gonna find a lot of creatinine, and you're gonna get like the impression that they need dialysis when really they don't, because they just exercised. They broke down the muscle, they have a lot of creatinine. This is not a steady state condition. Remember when I said that the endogenous substance must be in a steady state condition? It's because if it is not in a steady state condition, you're going to get the wrong impression that they need dialysis when really they just exercised. Okay? So again, the good thing about creatinine is that it's endogenous. We have constants, so we only ever worry about the concentration of the creatinine in the plasma. And finally, we make sure that the patient is in a steady state condition where they haven't exercised and they haven't released a lot of creatinine. Otherwise, we get the impression they need dialysis. Okay. BUN is basically blood urea nitrogen, which is honestly very similar to creatinine. Like the purpose for it is the same thing. We just get JFY from it as well. Only difference between it is the normal plasma concentration value for them. So for creatinine, we said that it has to be 1, but for blood urea nitrogen, it has to be 10. That's the only difference, honestly. And so like the 1 in creatinine is the 10 in BUN, and it basically gives us the 120 in JFY. Okay. Type. Now we move on to something called PAH, which is para-aminobutyric acid. Now, para-aminobutyric acid is an infused substance, so it's not really an endogenous substance, you infuse it. But the thing about para-aminobutyric acid is that it's freely filtered. And when it's freely filtered, it's also, we know how we said we have 800 liters of blood, 120 of which is being filtered, and then 99%, which is 179, is being reabsorbed. This 20%, the other like 80% is passing through the peritubular capillaries, right? So 20% getting filtered, but 80% is passing through the peritubular capillaries. Now, the thing about aminobutyric acid, which makes it really like distinctive, is the fact that even though it's being freely filtered and everything, but it's also being completely secreted. So whatever you like, the 80% that is passing through the peritubular capillaries is also being secreted, and it's entering the tubular system. So basically, it's freely filtered and completely secreted and excreted. So PAH can actually tell us the RPF, the renal plasma flow, because like basically when it's totally secreted, it's going to show us exactly what the RPF is. And this is really important because in pathologic conditions, for example, like renal artery stenosis, when like the renal artery itself is kind of tight, so the amount of blood that is going to pass through is going to be less than the normal. So basically, if the RPF normally is 600 and there's renal artery stenosis, you might get like 400, let's say, okay? And we can deduce from this that basically there's some kind of pathologic condition. If the PAH is not equal to 600, which is indicative of the renal plasma flow, we immediately think of a pathologic condition, okay? Yeah, another thing about the PAH is that it has something called a transport maximum. Now, I mentioned that the PAH will be completely secreted from the peritubular capillaries to the tubular system itself. But the thing is, at some points, if you infuse too much PAH, if there's a lot of PAH in the like artery in the plasma, that would basically cause the kidney to reach a transport maximum, where the kidney is no longer able to completely secrete the PAH. Therefore, what happens is that some PAH is left behind in the plasma, and basically this means that you infuse too much PAH. In other words, if the transport maximum has been reached, the plasma will not be completely cleared of the PAH, okay? If we just turn everything that I said right now into a graph form, this is exactly what it would show as. The filtration is basically the red line. As the plasma pH increases, the filtration will increase, and same thing applies for the secretion. But at some points, if we reach the transport maximum, it can no longer secrete any more pH, and pH is left behind in the plasma, and therefore it kind of turns into a plateau and it becomes constant. And excretion is basically the sum of the filtration and the secretion. And we can see that the excretion is going to increase as the plasma pH will increase. But at some point, when the secretion reached its transport maximum, the excretion will also curve around. But the reason that they're not curving at the same level is, and you see this like tiny difference in between, which is called display, is because we have a lot of nephrons. We have 2 million nephrons in every kidney. So it's impossible for every nephron to have the same exact transport maximum. So this is exactly why the excretion does not curve around at the same secretion level. Okay, so again, filtration increases as the pH concentration increases in the plasma. Secretion is going to increase as well up until it reaches the transport maximum, becomes a plateau, can no longer secrete the pH, and the excretion is the sum of those two together. It will keep on increasing up until it reaches the transport maximum. And the reason we have this display in between is because we have 2 million nephrons. Each one has a different transport maximum. Okay. Another clearance that we could have is the glucose clearance. Now, the glucose is actually a substance that normally should not be filtered. It should not even cross the filtration barrier. Glucose proteins, but in some pathologic conditions, you might have glucose in the urine. But normally, the glucose that is being filtered should be completely reabsorbed. So whatever is being freely filtered, it should be completely uptaken back into the peritubular capillaries and back into the plasma. It's very similar in pH in the sense that it also has a transport maximum. So, for example, you have a lot of glucose in your urine, the kidney might reach a transport maximum where it can no longer reabsorb this glucose from the tubular system up into the peritubular capillaries. And basically, glucose will only appear in urine in, like, again, pathologic conditions. That's called glucosuria, and usually that's the case for like diabetic patients. But again, glucose is freely filtered, completely reabsorbed. It also has a transport maximum where at some points the kidney might not be able to uptake more glucose from the tubular capillaries from the tubular system to the peritubular capillaries, and that's the case for like diabetic patients. Again, if we take this into a graph form, filtration is in red, so the greater the glucose concentration in the plasma, the greater the filtration will be. And reabsorption will also increase as the plasma concentration increases, but at some points it might reach a transport maximum and it becomes like stagnant and it forms a plateau. And excretion, we can see it only ever starts when the reabsorption hits a plateau, because it means that when not all the glucose is reabsorbed, that's when it shows in the urine. That's when it starts being excreted. And the higher the concentration of glucose in the plasma, the higher its excretion rate. When it comes to these like kind of graphs, you might get them in your exam. So honestly, just be very critical and specific about this. So although you might see like display like the excretion begins at 4, it's not really starting at 4. It's starting around like, let's say 3.75. Okay. So when they give you a question like this, they ask you when did this excretion start, like what plasma glucose level. Don't say 4, say 3.75. Okay. So this is for the glucose clearance. So we discussed technically 3 substances that are passing through the tubular system and how they can help us figure out multiple things. So for example, if we're talking about the para-aminobutyric acid, which we said is freely filtered, and all the 80% of the basically PAH that's passing through the peritubular capillary will be secreted, and therefore this helps us figure out the RPF, the complete renal plasma flow. And when we talk about inulin, inulin is freely filtered, but it's neither secreted and neither reabsorbed. Therefore, whatever is being filtered is also being excreted, and this gives us the JF4. Another substitute for inulin would be creatinine. And finally, we have glucose, which we said is freely filtered and it is completely reabsorbed. And again, glucose and PAH might hit a transport maximum where they are no longer able to be to secrete anymore for PAH or reabsorb anymore for glucose. Okay, but normally the glucose should only be 0. Like you should not even find glucose in your urine. Okay. Okay, this is a second checkpoint. I know we went over a lot of concepts. Do you guys want me to go over any of the concepts so far? Anything you guys don't get? I'd be more than happy to go over them. Do you guys don't get anything? Yes, okay. So basically for PAH, where did we start? Okay, yes. So the thing about I think it's like the numbers that are confusing you guys. Okay, so we said we have 800 blood, that is 800 liters of blood passing through, okay, through the renal artery. And then 20% of that is being filtered. 20% of 800 is 120 liters, okay? 80% of which are just simply not being filtered. Therefore, it just goes to the peritubular capillaries, okay? PAH, what it does is it basically gets freely filtered, okay? And all the amount that is in the peritubular capillary is secreted back into the tubular system. So all in all, the para-aminobutyric acid is completely being excreted. The amount that is being filtered is passing through, as well as the amount that is being secreted from the peritubular capillaries into the tubular system is going to add up to the total amount of 600, which basically tells us what the RPF is, what is the renal plasma flow is. Does that make sense? So all you need to remember is that it's freely filtered, completely secreted, and therefore PAH is indicative of RPF, the things that are in pink. Does that make sense? Yes, basically it's the maximum value. So the maximum value that you can have is the RPF, and the PAH is the only substance that actually tells us that, because it's freely filtered and completely secreted, which tells us that this is exactly what the RPF is. The maximum is 600 in normal conditions. Okay, that's good. Does anybody else have any questions? Okay, I guess I'll just move on to the next point. Now we're finally reaching the last part, which it might be a little confusing, but I'm sure you guys will get it. So it's basically called the fractional excretion. Basically, the clearance value of any substance can range from 0 to 600. So you asked me about the maximum. The maximum is 600. So this is why I'm saying the upper threshold, the upper end of the threshold is 600. And 0 is basically the lowest thing that can be excreted or cleared. If we divide clearness by JFR, we get the value of fractional excretion. So for example, if we divide the clearness of a certain substance by the clearness of JFR, which could be indicated by inulin or creatinine, then we actually get the fractional excretion. And the entire reason we actually look for the fractional excretion is because we want to know if there is a net secretion or net reabsorption. So for example, if the fractional excretion is greater than 1, then we have net secretion. And if the fractional excretion is less than 1, then we have net reabsorption. So for example, if let's say you're checking for urea, and urea is 0.4, so the concentration of the clearance of urea is 0.4, while the concentration of inulin is at 1. So 0.4 over 1 is 0.4, and 0.4 is less than 1. So we can say that there has been net reabsorption. On the other hand, if we talk about aminobutyric acid, which is 5, divided by 1, which is basically inulin, which is JF4, it gives us 1. The F and 5 is greater than 1. And therefore, we could say that there is a net secretion. So again, the fractional excretion is simply the clearance of a substance divided by JF4, or divided by inulin clearance, or by creatinine clearance, everything that is giving us JF4. All just to know what is the net basically movement. Is it net secretion or net reabsorption? Okay. And the fractional, same thing actually, it's the same thing that I just mentioned. Again, just that fractional excretion, if it's greater than 1, there's a net secretion. If it is less than 1, then it is net reabsorption. Okay. Does everybody get that? Okay. The final concept that we will go over is the free water clearance. Now, the water is a substance just like any other solids that we have, and therefore, we consider that there's also a water clearance for it. So, the free water clearance simply measures the amount of plasma that is completely cleared of water. So, we have a certain amount of plasma, and the water got cleared out, and it's now in the urine, and that's what we call the free water clearance. Normally, the concentration of all solids in the plasma must be around 300 milliosmol per liter, and if, for example, the amount that if we excrete plasma with all of these solids proportionally, then the clearance of water is 0, and this is why we consider the urine as isoosmolar. So, for example, we have the blood right here, okay, and let's say that some of this blood is basically made up of water, and then the other part is made up of the solutes. Now, usually the normal thing in the plasma must be around 300 milliosmol per liter, but and if you excrete the same amount, if you excrete the same ratio of solids to water, then we can say that the urine is isoosmolar. Why? Because it's the same thing as the one that is in the plasma. So we say that the urine is isoosmolar, plasma is isoosmolar, and the osmolarity of the urine and plasma is similar because the amount of water that we excreted in proportion to the amount of solids that we excreted are similar. They're the same thing, okay? But if, for example, we excrete more water than solutes, so for example, this is our water, it's much more than what we had, and the solids are the same. If we excreted this amount in the urine, then we say we have a positive free water clearance. I always think of it as, the water got out, the water is now in the urine, so now it's happy and it's positive. So we have a positive free water clearance because we excreted more water than the solutes. And therefore, we consider the urine to be hypoosmolar, while the plasma is hyperosmolar. Why is that? Because we excreted more water in the urine. That means that the proportion of solids to water is much less because the water basically diluted all the urine, and therefore we call it hypoosmolar. On the other hand, because we have less water left in the plasma, the solids are now more concentrated, so we call it hyperosmolar. So always remember that if the water is leaving through the urine, it's positive, it's happy, so it's a positive free water clearance. If we excrete more water than solids, they're happy, so positive free water clearance. And the urine is hypoosmolar in that case, but the plasma is hyperosmolar. And vice versa is also true. So, for example, if we excrete more solutes than water, then we get a negative water clearance. The water is left behind in the plasma. It's now sad, it's negative, so we have a negative water clearance. And the urine is considered to be hyperosmolar. Why? Because we have less water, so the proportion of solids to water is now higher because we have less water, and we consider it hyperosmolar. While the plasma is hypoosmolar because we left behind the water, the solids that are in the plasma are being diluted by the amount of water there, and therefore we say in negative water clearance, the urine osmolarity is higher than the plasma osmolarity. I know this is a kind of challenging concept, but do you guys get it? Is everyone good with that concept? Yes, exactly. So if urine is hypoosmolar, then plasma would be hyperosmolar. Always think of it that they're inversely proportional. So and the opposite is true. So if urine is hyperosmolar, then the plasma will be hypoosmolar. Yes, opposites, exactly. The opposites. And again, if the water is, if you excrete more water than solutes, then the water is out, the water is happy, it's a positive water clearance. If the water is left behind in the plasma, it's stuck inside, it's sad, it's a negative water clearance, okay? Does that make sense? Okay. And this is exactly the same thing, but we just turn it into like a formula form as well. So basically, if we calculate the clearance of all osmotic effective substances, so like all the solutes, let's say, we already discussed that the clearance is basically just like the urine flow multiplied by the urine concentration of the solutes and over the concentration in the plasma, right? So basically, if we take this equation right here, which is the clearance of water, it equals the complete urine flow minus the clearance of the osmotic effective substances, which makes sense because the urine flow is composed of what? Of water and the solutes. So if we take the clearance of water, it's going to equal the urine flow minus the clearance of the solutes. And again, same thing is that if the value of this equation is negative, if the value is negative, then that means we have a negative water clearance. The water is left behind, it's sad. And if the value is positive, then you excrete more water than solutes, the water is out, and the water is positive. So a positive water clearance. And just like you mentioned, the urine and plasma osmolarity are inversely proportional. So they're opposites. Okay, and these equations are really important to memorize. So I urge you guys to just memorize all of these. They're really important, okay? Does that make sense? Okay. Now, this is basically a summary of like all that we discussed, and it's just simply from Dr. Shams's slides. Here he's basically going over all the concepts, the formulas. So we have the clearance, which we said is the urine flow multiplied by the urine concentration divided by the plasma concentration. And then the clearance, which is basically calculated by the JFR, which is basically calculated by inulin or creatinine, because they're both freely filtered, not reabsorbed, and not secreted. So it just gives us simply the JFR. And we can basically estimate it from the plasma concentration of creatinine, which is a much easier way than the inulin because it's just an endogenous substance. And we also talked about the clearance of bioaminobutyric acid, which is freely filtered, completely secreted, and therefore equals the renal plasma flow. Final thing was the clearance, basically the fractional excretion, which we said is the clearance of a substance over the clearance of inulin, creatinine, whatever it is, basically over JF4. And if it's greater than 1, then it is not secreted. If it is less than 1, then it is not reabsorbed. Okay? And the normal values that basically they're really good to memorize. As you know from like CVP, you have your cardiac output, 25% of it is actually going to go to the kidney as renal blood. And then that basically means we have 1,100 milliliter of renal blood. And then 60% of that, remember when I said 60% is plasma, and then 40% is the cells that don't pass through. 60% of that is technically the renal plasma flow, which is 600 milliliters time per minute. And then finally we have the last two, which are the pulmonary filtration rates, which normally should be 120, which is basically just like the 20% of that 600 milliliter, or technically we can also say 800 liters, right? And 20% of that is 180. And finally we have the filtration fraction, which honestly just make sure that you don't confuse filtration fraction to fraction excretion, because the filtration fraction is JFR over RPF, while the fraction excretion is the clearance of a substance over the clearance of inulin. So normally the filtration fraction must be 20%. Okay, and we said that we check for the fraction excretion just to figure out if we have a net secretion or net reabsorption. Is that good with everyone? Do you guys get all the concepts so far? Okay. If inshallah you guys all get it. But if you ever feel lost and you don't get something, please don't feel free to contact me. I have my email and my phone at the beginning. Let's go over some questions. Now, all of these questions were actually from our exam last year. So, and you will find, I'll send it inshallah, and you will find all the answers in the notes section in the PowerPoint. So, does anybody want to read? Oh yeah, okay. Fractional excretion is just simply the clearance of a substance over the clearance of inulin. It's right here. Where is it? Yes. Yes, okay. So it's just the clearance of a substance over the clearance of inulin. If it is greater than 1, then it's a net secretion. If it is less than 1, then it is net reabsorption. So for example, if the clearance of we know normally glucose should actually be 0. Let's take another example. For example, let's say a clearance of any substance is 100 and the JFR is 120. So basically we're gonna get 1.2, which is greater than 1. So we say there's a net secretion, and the opposite is 2. Okay, so if it's a value that is less than 1, 0.5, then 1 is greater, and therefore we say there's a net reabsorption. Does that make sense? Okay, good. Let's go over some questions. So, does anybody want to read? Okay, so I guess I'll just read it, and you guys just let me know what is the answer in the chat. So, a patient is suffering from acute glomerulonephritis, and his glomerular filtration rate is reduced from 120 to 80. If the rate of creatinine production remains normal, what change in plasma creatinine concentration will occur? Okay, that's fine. Don't worry about it. But if you get the question, just let me know what's the answer. So again, the JFR was reduced from 120 to 80, and the creatinine, yes, exactly, it should be C. Good job. Because basically, when 180 is to 80 is basically decreasing. So we can't say increase, so we can just simply rule out A and E. And unchanged doesn't make sense as well because there has been a decrease. So it gotta be either C or D. And we rule out D because it sets continually without reaching an equilibrium, which doesn't make sense because if it kept on decreasing, that means it's gonna the JFR is also going down to 70, 60, 50. And if that happens, that means that the kidney is failing and we would need dialysis. But all that they said is that basically they just stopped at 80 and that's it. So the kidney basically adapted and it decreased to a no equilibrium level, which is below the normal. But that's it. So yes, it is C. Good job. Okay, so a second question is this. A healthy woman has a normal plasma glucose concentration. In which part of her nephron would the glucose concentration of luminal fluid be the highest? So some keywords here would be healthy and normal plasma glucose concentration. So where would the highest glucose concentration be? So just to recall, we have like the efferent arteriole going in, forming the glomerular capillary. We have the efferent going out, forming the peritubular capillary. Here we have the Bowman's capsule. In the middle, we have the Bowman space. And then here is where we have the filtration barrier. Yep, exactly. Good job. So it should be Bowman's capsule because basically it should not cross the filtration barrier and go to the Bowman space. If it did that, then there must be some kind of like pathological condition. But they did mention she's a healthy woman. So this is the exact keyword that tells us that, okay, she's healthy. So there's no glucose passing through. It did not pass the filtration barrier. And therefore, the highest concentration of glucose must be in the Bowman's capsule. Okay, good job. Third question says, creatinine, which is a product of muscle metabolism, is excreted by the kidney. Which of the following describes the correct handling of creatinine by the kidney during a steady state production of creatinine? So some keyword here would be steady production, sorry. C, yes, exactly. Mashallah, you get them all right. Yes, it should be C because we mentioned how creatinine helps us figure out the glomerular filtration rates, right? So technically, the filtration rate would equal the excretion rate of creatinine because we mentioned it's freely filtered, and then the amount of secretion and reabsorption are counterbalanced. So basically, they equal zero, and the filtration and excretion should all be the same. And this is exactly why we get the JFY from the creatinine. Okay. Now, the final question is this. An experiment, the renal vein of a rat was cannulated and a pH was infused. Following a sufficient period of equilibration, plasma pH concentration was 0.2, urinary concentration was 100, urinary flow is 1, and inulin clearance is 100. The fraction of filtered plasma at the glomerulus is which of the following? Okay, I'll give you a bit of time to solve, and let's see. Just to remember, filtered fraction is JFI over RPF, and JFI itself is urine flow multiplied by the concentration over the concentration in plasma of the substance. And then clearance then again is the same thing as JFI. So okay, so JFI. Okay, actually, let me just walk you through it so it would make more sense. Honestly, when you reach these kind of questions that have a lot of values and a lot of numbers, you kind of get intimidated and confused. But the best thing I suggest is just write down everything on the side. So they mentioned that the plasma PAH concentration is 0.2. So we can say that the plasma PAH is 0.2. And then they mentioned the urinary concentration was 100. So we just say urinary PAH is 100. And then the urinary flow itself was 1. And finally, they mentioned that the inulin clearance is 100. And remember that inulin clearance is technically just JFI, okay? And yes, you're right. So JFI is 100, so inulin, because inulin is 100. So now all that we need to do is just enter all of these values into our equation. Now they're asking for the fraction of filtered plasma. So we're talking JFI over RPF. And we already have JFI from the clearance of inulin, which is 100. So we just simply insert the first value in. All that we need to find now is the RPF, okay? So how do we find the RPF? The RPF would basically be given, we basically just need to find the clearance of the PAH. So remember how we said that the clearance is just the urine flow multiplied by the concentration of the substance in the urine over the concentration of the substance in the plasma. And because PAH basically gives us the RPF, we just find the clearance of PAH because PAH is indicative of RPF. So the urine flow itself is 1, and the concentration of pH in the urine is 100, and then we just divide it by 0.2. Okay, so let me just use my calculator. So this gives us 500, and then remember to just always insert your value back in. So a lot of like big mistake people do is that they stop here and they're like, okay, where's the 500? And they don't find it. Always check back and check your initial steps. So to find the filtered fraction that we wanted initially, we say 100 over 500, which gives us 0.5, okay? Is that good? Oh, I'm sorry. Yes, you're right, actually. You're right. It should be 0.2, you're right. The final thing should be 0.2, you're right. But does that make sense at the end? Does it add up? Okay. So basically this is it. If you guys can scan the code and let me know what feedback you guys can have for me, so I can improve, inshallah. But also I will send the PowerPoint which will have more questions so that you guys can practice. And it will help you orient yourself better when approaching the exam. Is that good? You're welcome. Okay. Please scan the code. Thank you so much.